All right, today I want to talk about Lab 5 and Chapter 4. So the midterm exam does not cover topics in Chapter 4. So that's, you don't need to worry about that for the midterm, but I do want to get started on Chapter 4. And so what I want to do is talk about functions. And I'm going to do that in the context of solving these two problems, 4.2 and 3.26. So this is your Lab 5. Before I get started, is there any question or issue that I need to talk about first? I'm going to just go in like this. So far, here's my Lab 26. So I actually made a video of this already. This is the problem where you have a grid of 10 vertical streets and 10 horizontal streets, and you have a simulated drunkard, so somebody who's drunk who starts in the middle of the grid, and then they take a random step in one of 4 directions. So we want to see, where this drunken person goes to under that situation. So this is what the code looks like when you run it. No, this is not right. This is problem 326. So here's this is the center of the grid, and each point here represents a place where the drunken person steps. And this, by the way, this has this is a kind of a famous problem in statistics. So it's called a random walk. Let's see, I think what I did here was I have a pause. So if you want to see it in an animated manner, then you use this this text in here, and I'll explain that in a minute. But I just want you to get to understand the problem. Here's the drunk who's stepping randomly, and that's what the result looks like. So if I run it again, we get a different result. And sometimes he walks off the screen, sometimes he stays in the center. Here he walks off the screen. Actually, according to statistics, that or probability, that this drunk will walk outside of the grid. The drunk will walk outside of the boundary of the window here with probability 1 as the number of steps goes to infinity. So maybe that's an interesting result. So if as you continue the simulation, the drunk will, in fact, with a very high likelihood, converging to 1, will wander away forever. In fact, we could test that. Let's see if that works. So here's we have the number of steps here. So here the drunk takes 100 steps. We can make it 1,000. So still in the center area. Coming back a little bit right there. Still hanging around the center. The program's still running. Hasn't really wandered off that much. You still see a little behavior over here. It seems like the center has wandered off. Let's try that again. So each time you run it, you'll get a different result. So here he wanders off to this edge here. It's coming back. So what I want to talk about today is functions, and this I already have the code for this. I suppose I should talk about this code as well. But what I want to talk about is how to reorganize this code to make use of functions. Let's see, how we can perhaps simplify the logic in this program, maybe to make it easier to understand by defining something called a function. So that's a task that I want to get to today. Now there's two problems I want to talk about that you need to do in lab. This is one problem, which is the simulated drunk. And then here's another problem. This is problem P42. This is a much smaller problem. So I want to start with P42. So we'll talk about functions and examine and solve this problem together. And then we'll go back to the simulation and understand that code and see how we might be able to use functions to simplify the logic. All right. So I'm going to create a new. Let's everyone take a look at that problem. If you have your book, 4.2. I'm going to go ahead and set up the project. This is 4.2. That's a console application. So the problem is to define a function called sort2. And sort2 takes two arguments, two numbers, and what the function does is it exchanges the values one for the other. So maybe there's x with the number 1, a y with the number 2. So x is 1, y is 2, and it exchanges those. So now x is 2 and y is 1. Let me get the boilerplate code for doing a console application. I moved some of the links around here. So it's a hello program. Just drop that right in there. Let's start by running that. I'll make this a startup project just to make it easier. Not necessary, but so we build, run, says hi. So here's the problem. What we want to do is, can I see your book just quickly? Because I got to remember exactly what it asks here. For 4.2, write a procedure, sort2, that swaps the values of A and B. If A is greater than B, oh, I see. Otherwise leaves A and B unchanged. And then it gives an example. So I'm going to follow that example, actually. Let's go ahead and just paste in the example. Can you read this out to me as I type it in there? I'm going to just put this code in here. So the book, they give you the test code. So was it int? Was it int u equals 2, v equals 3, w is 4, x is 1, oops. And then we call sort 2. So basically what we want to do is sort two numbers. Sort UV, and then what, print them out, is that it? That's all they have? Oh.
And then they do another sort with W and X.
I see. So let's do this. Let's print U. U equals U. And V equals V, and let's put a new line in there. So we see U is smaller than V. So if we want to, they're already sorted. 2 comes before 3. So when we print this, we should print this. We should print U equals 2. Actually, let's print before the sort. Let's do it like this. We're going to print before sort 2, and then after sort 2. So before the sort 2, U will be 2, and V will be 3. After the sort shouldn't change anything because they're already in sorted order. But if we were to sort W and X, then we want to exchange the values in W and X so that W becomes 1 and X becomes 4. So let's actually we'll just do it like this. Let's just try to make it maybe easier to look at if we do this. So we're just going to call this test case 1, and then we have a test case 2. But this should be W and X. This is W and X. There we go. So we have 2 test cases. See, the first case is when the 2 values are already sorted, and the second test case is when the 2 values are not sorted. And I think it's good to even put more test cases in there. What would happen? Yeah, we'll leave it like that for now. Okay. So this is a function. It would be something like, let's do this. Just to get this to run, we don't want to try to do the whole problem all at once. That's tough. Let's call a function that we know how it runs. So we'll call max, the maximum of 2 values. Actually, this doesn't do anything, does it? Because max returns a value. Let's see, illegal left-hand operator. This is before string. Oh. You see, I forgot to put the output operator there. So actually, max doesn't do anything. In fact, max returns a value. So we could do something like that, but we just discard the A. I'm just putting it in there. In fact, maybe rather than using max, let's go ahead and leave sort in there. Let's leave it at sort 2, because max doesn't make any sense. Just do it like this. I'm looking for a way to make the problem solution come out in steps. So what I'm going to do is just comment that out. That function needs to be created. It doesn't exist yet, so the code won't build and run. So I just want to see the test code, even though the test code won't run correctly. So that builds. Let's run it. So before sort 2, u equals 2, v equals 3, and then after sort 2, u equals 2, v equals 3, right? So we're not doing anything. We're just printing the values of the numbers. Oh, and this says before, so we need to fix that. See, the test code is bad, so this needs to be after. And I even spelled these wrong. Let's clean that up. Okay, there it is. Even hard. I'm going to put the, just to make it even more clear, I'm going to do this. I'm going to do C out, the lowercase c, or it's case sensitive. You got to use lower c. This is test case 1, and I'll put a new line there. Yeah, we're going all out with the. And you know, when I there's an issue about comments, right? Someone suggested that I use more comments in my code, and there's a debate going on about commenting, right? So I mean, in general, commenting your code is good, but here's an example where it's a judgment call. Maybe it depends on the team you're working on or your personal style. Look at this comment. I could do test case 1 here. This comment. Does that make it easier to read the code or harder? Well, in one sense it makes it harder, because now I have to read, not only do I have to read the line, not only do I have to read the code here, I also need to read the comment. But the comment and the statement are so similar to each other, it's redundant. So you could make the argument that this comment is distracting or unnecessary, just makes more lines of code to read. On the other hand, when your eye scans through the file, it could just skip over statements and just read the comments. From that perspective, it's better to have the comment in there, because then you can just skip through the file and read the comments. Which way is better? Anybody have an opinion? Actually, I don't really have an opinion. I know that both ways work. But I know one thing, that in a project or in an individual program, it's better to be consistent. So if I'm putting in a comment for each block of logic, even if the comment is kind of redundant in terms of the, in other words, it's easy to read, to know what's going on by reading this one line of code. So if I start putting comments in to label blocks of logic to make it easier to read, I want to do that everywhere, not just in one function or one place. I want to do that everywhere in the program, so that as you start to work with the program, you see the style, you see the pattern that the programmer is using, so then you can start processing the code more easily. So I would argue that the important thing is that that whatever policy or tendency or pattern that you're going to follow regarding comments and regarding anything else related to structuring your code should be consistent. Then it becomes easier to read. Your comment?
Along the same lines, I like to put spaces between different portions of my code.
Yeah.
Does that matter?
Like blank lines you're talking about?
Yeah, just blank lines.
Well, look at, I'm very deliberate about my blank lines. You see, so this is a block of logic here. This is test 1. And this is in fact test 2. And this is just a separating new line. So in the output, I see test 1 and test 2 separated. So this doesn't belong to test 1, nor does test 2, so I put blank lines above and below it. So I don't know if my line spacing looked random to you. But I'm very deliberate about my line spacing, and I look for consistency. The line spacing is very important. One thing is line spacing, the other thing is indentation. You could see here these symbols here are fully to the left. And this is an opening brace, this is a closing brace, and everything that's within that function is indented. So the indent shows that inclusion, that this logic is a part of that function. The only way this code is going to run is if that function is invoked. And of course, if you have an if statement, right? Normally you would do something like if u is 2, then print something. You can see Visual Studio even generated that indent for me. I didn't even do that indent. So it's so common to use indents, and it's expected by the reader of the code. The reader of your code is expecting for it to be indented to express the logic and the dependency between different operations. So the code that's in this spot here, is triggered or run or executed only when the condition is true in the if statement. So we indent it and show that dependency. So here we have 2 levels of indent, right? So we have one indent, the if expression, the conditional, they call it a conditional. The conditional is inside main. So we indent it to show that it's in main. But this cout operation is inside the if, so we have to do an extra indent. So there are 2 levels of indent here. And one of the problems you're working on right now that's due tonight is that prime number problem, where user types in a number, I think, and then you have to generate all the prime numbers between 2 and the number that the user specifies. So there you're going to need to use a loop within a loop to solve that problem. So that inner loop, so your code is going to look something like this. You're going to have a loop here with some loop condition, and then you're going to have another loop. Visual Studio doesn't know what to do with this code because it doesn't parse. But, well, it knew what to do there. So this is what you need to solve that prime number problem. Is that 323? Is that the one? I think it's 323. 321. 321. So this part of the loop here is check each number between 2 and n, where n is the number that the user types in. Maybe n is 7. So that means you want to print 2, 3, 5, 7. You want to skip 4 and 6 because those are not prime numbers. So how do you do that? So this outer loop runs through, let's call it k. Start at 2. And let's stop at n, and we'll increment k. So we're going to look at each number between 2 and n. Let's look at each number between 2 and n. And now we have this inner loop. So that's the responsibility of the outer loop. Look at each number between 2 and n. Okay, so on the inner loop, we have k. This is determine if k is prime. If k is prime, then print k. Else don't print k. You see how that works? So you have to think in levels. The first level, the outer level, is examining each value, 2 through n. And then once you have that established and fixed in your mind, and you have this variable k defined, then you can forget about the outer loop. And in here, you have k. And this inner loop here, which determines whether k is prime or not, we don't even need to think about n. N is just the limit for the outer loop. So we can just sort of drop that from our minds and just say, OK, we have k. How do we know if a k is prime or not? And we use a loop to do that. And we try to divide. Look at this. Divide k by every number from 2 to k minus 1. So try every number. You need a loop. You're going to try 2, we're going to try 3, we're going to try 4, we're going to try 5. And if any one of those numbers divides into k evenly, then k is not a prime. We don't print it. But if we finish this loop, and if we finish the loop so that every number that we try dividing k by gives us some remainder that's not 0, then k must be prime. I'm not filling in all the details here, but just giving you the overview. You've got a loop within a loop. There's some more logic that you have to work out in that inner loop. I think John was helping some of you, and he suggested doing this. Define a variable called is prime, and let's set that to is prime is, do we set it to true or do we set it to false? We set it to true, that's it. And as soon as some number divides into k evenly, then we set is prime to false. And then we have to add this logic out here at the end of the loop. If is prime, then what do we do? What would you do? Print k. Right. The only time you're going to print k is if is prime remains true. So we set it to true here, but if we discover a number that divides into k evenly, we set is prime to false right there. So we don't print it. By the way, this is one way to do it. You can do this without a variable is prime. I mean, I would do it without is prime, but maybe this is the easier for you to tackle, right? Because there's other commands. You can use a break. I would probably use a break statement. Yeah.
Do it by if you divide by 2 and there's a remainder, and if you divide by 3 and there's a remainder, print that number. So that's what I did.
If you divide by 2 and there is a remainder,
and you divide by 3, because that's a prime number.
So if you divide by 2 and there's a remainder, and you divide by 3 and there's a remainder.
If you divide by 2 and there's a remainder,
Yeah.
it means it's an odd number.
Yeah.
And an odd number is a prime number if it's not divisible by 3. So 4
Aren't there odd numbers that are not divisible by 3? 35, there we go. 35 is not divisible by 3 or 2. So you got to divide 35 by 5.
That's what does, like check every number
Yeah.
from 0 to 8.
Actually, you only need to check every prime number from 0 to, that's what you're thinking probably. But how do you have to know what the prime numbers are to do that, so we don't.
Well, you only have to check every odd number.
Well, that's because 2 is prime, and then you need to check every third number because 3 is prime, and you have to check every fifth number because 5 is prime. You have to check every 11th number because 11 is prime. So you have to extend that logic a little bit. This is a good exercise for the math majors. That's why I picked it, because I know there's a lot of math majors in here. Okay. Any other discussion on this before I wipe it out?
There's a solution in the book also.
There's a solution in the book? There is?
So the idea in this program is to
It's
just
210, page 210.
210, they have a solution? Well, it makes the problem easier.
Yes,
So all we're doing in this program is just inputting two numbers and putting them in
No. Input one number, n. Actually, I don't even. Do they ask for an input of a number? Yeah, and that doesn't matter. That's the unimportant part of the problem. So you just have to know what n is, and so that's what the user inputs.
yes,
Huh?
yes, hard one.
This is a hard one.
Yeah.
Yeah, but this is your first opportunity to really understand what it means to write an algorithm, to solve a problem with an algorithm. So this is the problem of coming up with an algorithm. You know, a sequence of steps, the instructions needed to solve a problem. That's an algorithm. So algorithms become a very important study later on. If you go to study more about computing, they study about different algorithms have different properties. Some algorithms are efficient at solving their problems. Other algorithms are inefficient. So then there's the problem of how do you come up with an efficient algorithm to solve a problem? And as the problem size grows, how much time does it take for the algorithm to complete? That becomes a very important problem. So a lot about what computer science is a study of algorithms. And the discipline of computer science started in math and electrical engineering. Those are the two places where computer science came. So originally these topics were studied in math departments. So there wasn't such a thing as a computer science major. It was you were either a math major or you were an electrical engineering major. Then you would study these topics. And then over time, there was such an explosion of computer use and theory, the theoretical development of computer science, that I said, let's create, we have a new discipline has emerged. It was like in the 1960s, something like that. It's slowly, now pretty much every university has a computer science department all over the world. So it's a very new discipline actually, even though it's 50 years old roughly. But that's pretty young compared to math. Okay. Let's come back to the sorting problem. And actually is it really on that page? Is that the solution to the prime number problem? Oh, it shows the problem solved using a function, right, Ati? On that page that you gave us. Yeah, this is chapter 4. So the problem that you need to solve was given in chapter 3 without.
Previous pages, there is another solution without the program.
Oh, they show that. That's what I was going to do today. I couldn't believe it. So it's. Did you see the picture of the first bug? This is the first computer bug on page 205. The first computer bug on page 205. The first computer bug. Here's the first documented computer bug. the program was malfunctioning was because this moth had crawled into the electronics of the computer and it was malfunctioning. So they pulled the moth out and they documented the problem. This was a time when computers were first invented. People didn't think much about mistakes in your code, because they were so much down at this low level of getting the logic to work, and there was a very weak understanding of where all of this was headed. And it turns out that finding bugs in your code and fixing mistakes is this enormous problem, and what so many people do with their lives all the time. So this is a kind of a funny starting point for finding bugs. There's a very interesting character. She's the one that found this bug, or was on the team that found the bug. She's quite an interesting character. She developed the first She developed the first compiler. So we're using, in C++ language, we translate that to machine instructions. That's called a compiler. And she developed a compiler for a language called COBOL, which is a widely used language in business. It's still actually running in many systems around the world. Okay, let's see. Let's come back to here. Let's look at this sorting problem. Now here, the chapter 4, what we're going to do is define this function. And it's going to look like this. What do they have? A here, right? And they have B. Is that what it looks like? So I'm going to build that. So look, I didn't do anything, and this is called a stub. So the program runs, but it doesn't run. It doesn't sort the numbers. So this is called a stub, and this is a technique that you use when you write programs. You don't have your entire solution laid out in front of you all at once. So you create these functions that you will be used to do something essential, but you're going to fill in the details later on. Let's just put the function signature there and an empty body and see if it builds and runs, and then we'll dig into the details about what needs to happen inside the function. The function has to swap A and B. If A is bigger than B, let's swap A and B. So there's the condition. If A is bigger than B, then let's swap A and B. How do you swap A and B? Let's think about it like this. Suppose you have 2 cups. You have a cup of grape juice and a cup of apple juice. For some reason, you want the grape juice to go in the cup that the apple juice is in, and you want the apple juice to go in the cup that the grape juice is in. You want to exchange the two. How do you do it? Can you do it? Throw the and catch this. That's not going to work. You need a third cup, right? So let's make a third. And here we need a third variable. You can do it without a third one, using the swap function. Well, the swap function uses another one, so.
Like A is equal to A plus B, then B
Oh.
equal to A minus B, then A equal to B. So yes.
Is that right? So you could do A. So you can actually add A into B, and then take B out of A.
A from B, then equal to B, then just A equal to B.
That's neat. That's right. I remember that. Let's do this one first, then we can come back and look at that. So this is the easy one. That one's the tricky one. All right. Let's see here. So I'm going to call this temp, And let's put A in temp. And then so we're preserving A, so that means let's put B into A. And then what do we do? Let's see. I put the grape juice in this third cup. So I emptied out. I put A into temp. I put A into temp, right? So now A is free. So I'll put B into A. Sorry, put B into A already, right? Now I have to put. Yeah, sorry, I got to put temp into the other one, right? So B is temp. All right, let's see if that works. It doesn't work. What happened? Did we do it wrong? How come it says it doesn't look like it got sorted? I really don't know what's wrong. So if A is bigger than B, then I want to put A inside B, which I do here, and then as if we did this totally wrong, right? So here, oh no, we put A inside temp. If A is less than B, then we swap? I thought A was supposed to be first, right? I don't think it's that.
Yeah,
Now I have U is 3 and V is 2. So now it's I want to go the other way. I want to go, from low to high. So 2 to 3 is good, but this should be 1 to 4. Maybe it's the test code is bad. Is the test code bad? Oh, the test code. Look at that. You know what? There's this big thing about testing. I got a recent graduate. He just got a job, some mobile phone software development company, and he says, he's very excited about what he's learning there, and he's saying, they're really big on what do they call it? Test first programming, or test driven system development. So before you solve the problem, you write the test case, and then you implement the solution. And my critique of that, and I do a lot of testing. Obviously, I'm writing the test cases here now. But the problem is if you have really a test-heavy project, which a lot of people think is great and what you should do, not only are you debugging the code that you're using to solve the problem, but you also have to debug and maintain your test code. And that becomes a significant problem. So I'm not gung-ho about test-driven development for that reason. And here we just see an example right here, right off the bat. There should be X and W. So we have a bug in the test code. Our implementation is okay. And as we continue to build out the system, there may be problems with our test code that needs to be fixed. So now we're going to debug even more. Nevertheless, you have to write test code sometimes. It still doesn't work. Huh? Oh, W is first. Yeah, that's right. W comes before X. All right, so there we go. We just debugged our test code. All right. So that's an example. Now this function here, this is a different kind of function than, say, max. If you were to write, let's write our own max function. Let's call it my max. if A is bigger than a B, then A is the maximum, return A. Else, B is the maximum. Let's return B. See that max function? But this is different than the other function, and the reason I'm doing this, I want to compare these two functions. This function doesn't return anything, so we declare it as returning void, which means it doesn't return anything. But this function here has a return value called, which is of type int. And the other significant difference is this ampersand, which is included here but is not included down here. So what is that ampersand about, and what is this int about and this void about over here? So let's talk about that. But first I want to test this myMax function. Let's get that to work. And I'll put that here. Well, actually, let's put it down at the bottom. So we have u and v and x, w and x defined, right? Actually, let's do it like this. C out. I'll put another space in here. And I'll do this. This is test case. This is test case 1. This is test case 2. And this is test case 3. And this is for, sorry, just going to clean that up a little. Let's put another blank line in between these two test cases. Let's see out myMax of 4, 8. And here, let's see out, for test case 4, let's see out the max of 14 and 8. Or 14 and 9, say. Or 14 and minus 9. See, what we're doing here is, let me write it a little bit easier. So this will be this, I'll call it the max. So I declare an integer, let me make it easier. I'll call it k. Now I'll call it the max. And so we call the function, I just want to make sure everyone understands what's going on here. We call the function here myMax, and we pass in two arguments, which are integer values, 4 and 8. They're not variables, they're numbers directly, literal numbers. And then this thing returns a value, and this symbol here, equal, you need to think about that differently than the equal sign you see in math. In math, it says that the thing on the right is the same as the thing on the left. But in programming languages, it means the thing that's on the right, which represents a value in memory, take that value from that place in memory and copy it into the memory that's labeled by the thing on the left. So actually, this is a function call. So at some point, the value of that function is an integer, and it's stored somewhere in memory, and that value is then written into the memory that's labeled with this name. Does anyone know how big the memory location is that this label represents? How many bytes large is the memory that the label the max represents? In a 32-bit machine. Actually, in a 64-bit machine, I think it's the same. but in C++, int doesn't have a precise size defined, but I think by convention everyone is using 4 bytes. But in better languages like C#, or Java, then there's an exact size that that an integer represents. So that's 4 bytes. This is 4 bytes. An int is 4 bytes. And so the function returns this value. This is different than sort. Look, sort doesn't return anything. That's why we declare sort as void. What sort does is sort operates on the variables passed into it. So when we call sort2, passing w and x into it, sort2 modifies what's stored in w and what's stored in x. See, sort2 modifies the memory that w represents and the memory that x represents. What if we did this? Look at that. Let's do the same thing that we did with max. Let's just put those values in there. What do you think's going to happen? Look, you see the red marks? This Visual Studio is wonderful. Here's a mistake there. It's not going to compile because 2, 4, and 1 are string literals. And the way we declared sort, that sort must take a variable, because sort operates on the memory that the variable represents. Here, the literal numbers 4 and 1 don't, although they are represented in memory somewhere in some sense, they are not labels for memory locations. They are not variables. So this will not build. And we see it already. One has failed here. Can I convert parameter 1 from an int to an int reference? Let's get rid of the reference. Now it just takes 2 ints. And also w4 and 1, right? So remember, to sort, it should print 1 and 4. But look, it builds now. It builds now. Well, what's going to happen? Is it going to come out sorted, or is it going to come out not sorted? Not sorted. And that's because in this formulation that A and B are no longer references. These represent new memory locations. And the value here, these literals, 4 and 1, those values are, when this function runs, the computer allocates 2 new integers and copies those parameters, those arguments, into those 2 new memory locations, A and B. And then then the A and B, which is what we call it local to the function. This code inside sort2 operates on the memory A and B, which is now local to the function and is not accessible outside of the function. When the function returns, that memory is discarded. This is a hard concept to get. So it's something that if you don't get it right in this moment, you'll eventually get it. So be patient, but you have to think about this. And you need to do experiments like I'm doing right now to really become confident about your understanding. And beyond that, you need to study like compilers and computer architecture to really know what's going on underneath the hood here. Because we're driving the car, we're not building the engine right now. But if you want to dive more deeply into the subject, you got to start looking at how the engine is built. What does the compiler do with this code? How does it translate it into machine instruction? That's not a topic for this course, though. It's a topic for a course called Machine Organization, Computer Science 313, for those people who are going to take that. And also another course on compilers that we teach here as well, Computer Science 570, covers this, and several other courses touch on this topic. So this is not the formulation that we want. This is the formulation that we want. So now here, when we put those ampersands in there, we're saying to the compiler, don't create new memory locations A and B that are local to this function, but let A and B represent the memory locations that the calling code is using. So now, with the ampersands, A and B represent the variables that are used when we invoke sort 2. But these are not variables. That's why it doesn't build. So we have to pass in variable names. Sometimes this is referred to as a procedure, because it doesn't return a value, and that a function is something that returns a value. Although that sort of definition of the word procedure and function is old, I wouldn't say it's that commonly used anymore in a precise way. So you don't really hear the word procedure very often, but you hear function, and this would be referred to as a function. Maybe the book calls it a procedure. I'm not sure. The book probably talks about this, but it's a bit of a historical concept. So let's look here. This is we examined sort. Let's take a look at max. So max, look, no problem here with max. We can call max with these numeric literals 4 and 8. We don't have to call my max with variables, although we could. And the reason we do that is because my max allocates memory to hold its parameters A and B. So you can pass in those numeric literals. And those values are then copied into the memory locations that are represented by A and B and that are local to this function. When I say local to the function, I mean A and B here. See the A and B in this code? This memory that's represented by this A, the memory represented by that A, can only be accessed by code inside these braces, the opening and closing braces of the function. This code here is the only code that can operate on that A and that B. That's why I would say it's local to the function. If we want to make it global, so that all code throughout the file can access it, we would do something like this. We could declare A and B like that, and then this A can then this A in the function then can access this value, and then code down here, the A down here would also reference the same A that this function is referencing. So these variables have global scope. They're defined outside of a parameter list. They're defined outside of a function. They're given global scope. So the function has, see this function with a void, there's no return statement, although we could put one in there. We can put a return in here. No problem. But when we return, we don't return any specific value. We just say return. So these aren't even needed. Although, it could be that you want to do some operation down here. And so you maybe put your return statement in this if statement so you don't execute that. That's one way to do it. So these returns are not needed, although they're acceptable. But in this case, let's suppose we didn't have a return statement in this function. The compilation failed. Why? My max, here it is. My max must return a value. See, we told the compiler we're returning an integer. So when we failed to return an integer, the compiler complained. Says you can't do that. So the A that gets passed in here, right, gets a copy of the calling code's value, and then we operate on A and B in here, and then here we return A. So if we modify A, we're going to modify the local copy, not the copy that the calling program passed into us, and then we're going to return the modified value. So here it is. We call the function, store the return value, and then print the return value. We tested this, right? Just look at that. So 8 and 14, those are the two maximums. 8 is the max from these, and 14 is the max from those. I'm giving you a lot here with functions, because this concept of a reference is a little tricky to understand. So I'm pretty much giving you the whole thing here. There's not much more you need to know to fully digest this, although there are some other strange behaviors and syntax that you need to learn about as well. But this is the bulk of it right here. The difference between a variable that's a reference, a parameter that's declared as a reference, this is a reference variable, and a parameter that's not declared as a reference. And this, by the way, this is in all languages, practically all languages. I mean, in scripting languages you might not see this, but the big languages like C# has this distinction, and Java, and PHP, name those languages. So this difference between a reference variable or a reference parameter and a non-reference parameter is a very important distinction to understand. Any other? Am I missing some concepts here? I want to discuss this anymore? We're done with this? And because we're kind of low on time, I'm not going to talk about 326. I have a video that kind of walks you through this solution, and today I was going to show you about how to perhaps reformulate this program using a function. So maybe we'll do that next time, maybe not, depending on what people need. But there's on that chapter 4 that those pages that Ati recommended, they show how to reformulate the solution to that prime number problem using a function call. So that's a very useful section of pages to read through and understand. All right, so help you understand functions better. Anything else? I mean, I have nothing else to say. Okay, we'll see you all.